Yeah. That's what it seems like. No one is there. I think mask gets difficult when you start sweating. I did grade and use few things for the course. Let's see. I did grade the submissions for the online course. That's the organization.
What was homework 7 drop for?
Oh, I didn't drop homework one, I dropped the lowest.
Oh, okay.
So I thought by now we had enough homework. There are a couple who are losing because of homework. So I thought this is a time to, like, sometimes people start giving up because of their grade at this point. So usually I drop it at the end stage, but then by the time they have already given up on the course, kind of. So this is just to point out that there is still possibility. The curve was very weird. The performance was pretty bad from my perspective. So, but I tried to not.
Do you mean performance for the exam?
Performance for the exam, yes. Yeah. Except Luke, I think, and actually Jordan got one of the questions right. Otherwise, no one got anything right. That's pretty much what I can say.
Now I feel bad for not submitting
But still, I graded the first. I mean, it's not that I did grade it like it should, and then I curved it, which is horrible because it's almost opposite of curving. So, but yeah, that's what it is. That's
So I think.
it. Right?
yes, Jordan.
So I think you said at the end of your lecture not to worry about studying, the conservation stuff, conservation and momentum. You said that would be the take-home part. So I think.
Yeah, that's what
probably
others were also saying. They studied a lot on the questions that I made it take home. Correct? I think that's what Alia was pointing out, that all the questions that I suggested became take home, and they all came prepared for that, especially that the legendary polynomials and the one you're talking about. So they were probably trying to guess what could be the problems. And yeah, I agree. There was a, yeah, I did agree to this last time also, that there was probably a misjudgment on my end, that what you will be prepared and what you won't be prepared with. But it was also that the first question, especially, I think I did want to give an elementary one. I felt there should, and I would say that some of you guys did try the right way. So I give good points. So yeah, maybe that should.
I probably should have solved that problem from just using, just solving it how I would have solved it in the past before this course. But I think I tried to solve it using the methods that you taught in class. So
Yes, I noticed. And that is harder.
Yeah,
Right?
I spent a lot of time doing it that way. Which,
yes.
if I would have done it the other way, I probably could have just wrote it down much quicker and got full credit. But
Probably, yeah, I agree. So, but then I don't know. So, like,
yeah.
I feel in an advanced course, like those are, for example, in a qualifier, that question, first of all, that question is too simple for a qualifier, I think. But still, certain things, at least from my perspective, I can say when I'm being very hard, I can say that, oh, no, that you should know just because you're in the course. But then I also understand what all goes on during an exam. As you're saying, you expected that you should attempt it using the methods that you studied now, and it should come out. And yeah, Jordan, you were not there last class. I think Luke was saying that he also did the same thing. So he struggled a lot with the first question, but he could proceed and actually get it done. But that's not really straightforward. Yeah. So, but I agree. The first question, I think I don't have too much. I don't want to apologize too much. But second, and especially third one, I would say, yeah, it was a little hard, I would say. Third one was hard. But
I did not use that F is equal to minus gradient of U. I used the idea that we did in 320.
yeah, that's how we should do. Yeah. So
I
you should
have
get
that.
it.
But
But you didn't submit.
Yeah, I didn't submit because I didn't
That's
know.
an excuse.
Because I didn't know how to do number 2. I got 1 and I was like, hey, I should not get 1.
So yeah, so this is a simple thing I can say at this point. If you got the first one wrong, and there's you don't have to mind about it, but if you got the first one wrong, I would say you have to really, that means that you're not completely understood the fundamentals of the course, like the concept that we are digging onto. Second one, I would say you are not comfortable with dyadics. And that's one of the elementary questions you can ask in dyadics. So you're not comfortable with dyadics. That's possible because you don't see dyadics everywhere. So that's, and third one is, I wouldn't say it's a hard question on vector calculus. It's a hard question and it's a tricky question also. So third one, I would say I would give it. But second one, you should be able to do it if you've come this far in the course. I would expect you to. And again, that doesn't mean that I'm making an opinion. And the first one, you should know it because you come this far in the course on electromagnetism. That's the way to put it. But after that, it doesn't mean that you should get everything. It's tricky.
One thing I would like to say, take-home problems are not that hard.
No, that's not correct. That's because I announced it and I made it. No, that's not correct. That's because you have learned the technique. It's like saying that I teach you to do one way and I ask you to do the other way. I can ask very hard questions. No, that's very hard. That's what we're learning. The take-home part is what we're learning in this course. That's a new technique we're learning. That's the understatement. I would say understatement that it's easy. I hope others don't. Like
not experienced in this being easy.
yeah. So you practice it so much that it is easy. But to say that the generic polynomial.
I did not say it is easy. I just said it is not that hard. It's
reasonable. Yeah.
I have a question.
Oh yes. Aliya?
Yes. You drop one of the homework.
I got what?
You dropped one of the homework. So can
That's correct.
Mhm.
Oh,
What
you're
happened?
asking why?
Yes, please.
Oh, I thought it will help others. That's all.
Okay.
No, I mean, if there is a complaint, I can take it back.
I just want to know what is the reason for that. That's it.
Yeah, so the point is, at this point, I am afraid that sometimes people give up on their grades. They think that it is hopeless to work for it anymore, right? So usually I drop the grades at the end of the course, and I realize that that is not the right time to do it. Sometime before helps, so that students have their correct grades in their mind. So, and this time we have had about more than 6 homeworks. So I thought it was reasonable to drop one. But if any of the good students who did very well in the homework, they think it is not fair to them, I might have to reconsider. I hope you're not saying that.
No, I thank you so much. I did that for helping us. Thank you so much.
Okay, that's, yeah. Okay. I have Alia's and Luke's papers, anytime when you come, you can collect it.
Okay.
Okay. And I have one more point to discuss, and that is that the exam was scheduled for November 9th, which is a Monday. Correct. And right before this Monday, the Friday, Thursday, you have the math methods exam. And I felt that there were comments that was getting too taxing, that 2 exams in a relatively close period. So I think it was Moses who suggested that we make it on Friday, but then it struck me that Rob is not usually available for a longer period on Friday. So I was going to suggest that you do this one week down, which gets closer to the final exam, but in the number of lectures. But
Should it be November 16? You should.
Yeah, because here it is Friday. So yeah, 16. I did correct it on the video. I hope this doesn't disturb any plans. If you have made any plans before with any of the dates, Rob.
That's good.
Okay, Jordan, Rob and Jordan are the ones.
As long as it's in a class period, it should be fine for me in terms of.
Yeah, and it's encouraged that it is in the class. And yeah, so let me know if that is, and yeah, Michael, but by the time I think Michael would have come back. Okay, so there's a homework aid I have posted on what we studied today and on Monday. Okay. Oh, I did not put the camera on. Why is that? So you guys are not able to see what I'm writing up. Oh, bad.
I have one quick question too. So I think one of my weaknesses in your courses is that.
Oh, you were not part of them.
Sorry, John. Yeah, go ahead. Yeah.
I think one of my weaknesses in your courses is that I don't get the opportunity to see enough questions formulated in different ways. And sometimes I think I get stuck thinking a little too long on exactly what you're asking before I can even write something down. I guess I have to really consider what you're asking. And so is there a good book that asks questions similar to what you're asking that I can just, work the problems in each? Like I know Schwinger's book, but I looked through some of his questions and.
Yeah, so here is what I suggest. I think this came up while discussing with one of you guys the other day. And it is very close to what I say to my undergraduate students, but with a small change in the context. So here is how I think one can judge yourself about the understanding of the course. So let's say that hypothetical situation that you are attending my lecture and you go back and you look at the homework and you exactly know how to do completely and you do it, then I would say there is a good chance that you have understood the course material and there's a good chance that you should be able to do other problems also. But most of the times that's not what happens. Even after you've attended the lecture, You probably don't know how to formulate the question. You don't even probably know what the question is asking about. That should be natural. But then you look up your textbook, right? Textbook or any book that is available to you. That should be okay. You use the internet, any resource that is available to you, and do the homework again, right? And after that, usually what I tell my undergraduate students is that do another problem. Pick your favorite problem or a random problem, and you should at least know what to do. It's not that you don't have time to work out every problem. In this case, it's not a different problem, but I say take any section related to any textbook related to this, or any section of a textbook related to this course. And you should at least have a feel for what's going on. Like you should be able to glance through the pages and say, oh, this is what they're talking about. Then I would say that that's good. That's what should be a test for what you learned in the course. Like, for example, I would say Jackson's book, you should feel comfortable just looking. I'm not saying that you should be able to work out every problem. That's usually hard for everyone. But if you want a simpler book, let's say Griffiths is a simpler book, or Stratton's is a great book. And these problems, again, you guys don't have time to go through every book that I'm suggesting. That's reasonable, but even though that is an expectation at a graduate level, but at least you should have glanced through them and see that, oh yeah, I know what they're talking about. They're talking about a disk. Oh, that's not solvable. So, but I might be able to do it using them. I might be able to. Have you attempted it? Probably not. But you might have a feel for, oh, this ideas will work there. So does that help you, Jordan?
Yes, but this is how maybe I should formulate my question or statement like this. So, for instance, you worked the disk where the observer's on the z-axis and when the observer's not. When the observer's not, then it's not a solvable problem, but if you can orient such that the observer's looking from the z-axis. So had you asked a question about a disk, sure, I think most of us probably would have easily been able to solve that. So my question is where can I find a good resource to work all such problems where you have surface charge on a sphere? But when you look in Jackson's book, it's some of the problems.
Hidden. Yeah, I agree that it's hidden inside in the sense that you cannot open the Jackson's book and see that, oh, these are the problems that's there, because only when you read it very carefully, you see what they're asking. I agree. I would say if you just want the titles, okay, if you're ready to pay that, and this is what I do often, at least in the last 2-3 years, I've been doing this. And if you go 100-year-old books, they have sentences long section names. Like, for example, a section, we these days say legendary polynomials, that's it. And then there are subsections that doesn't even come under table of contents. So there's one small advantage, even though old books have a very different notation, they don't use the vector calculus like we do. Like they actually explicitly write the component. So don't try to read the textbook. I don't think it's a great suggestion at this point of your learning, but you can, I will encourage you guys to look at the table of contents. Each section is sentence long. They say electric potential due to a ring, uniformly charged ring at a distance r. So you know, oh, that's what they're talking about. One sentence is a good summary of the whole section. It's like an abstract to a paper. So look up old textbooks. I would say that Maxwell's book is not bad. Maxwell's original book is not really bad. Like table of contents, notations are not great, but content-wise, it is beautiful. Even today, I would say I like it very much, but it is, vector calculus is not done in our style, not in the modern style. So it's a huge price you pay, but interpretations are very, very good. Even today, they stand the, at least for teaching level, they stand it. For research level, probably not. So Maxwell is one, then there is Heaviside. So I can list it. So these are at least the books that I like. So if that helps at all. I usually don't tell this because I thought students might get overwhelmed with So I would say Maxwell I've been doing, for the last 5 years, I've been using Heaviside's book. It comes in 3 volumes, like Oliver Heaviside. This is in, he did most of his work in 1880s, like right after Maxwell. And then, it is easier to read this because the lot of vector calculus or modern notation is there because he's the one who introduced that notation. So he's a good book and interesting guy also. There is you can read about him also. He's the same guy whose Heaviside step function, and he also has units in electromagnetism, Lorentz Heaviside units, like we have Gauss units, SI units. His work was good enough or voluminous enough that people have to depend on him. Second is Abraham's book. This is less of what I've used. Abraham. This is Abraham. That's I don't know the title of the book. Probably electromagnetism. He was in the same time period, 1900s. I like it because the early part of the calculus he has done very well. And the third is Maxwell. That's for the last, I would say, 1 or 2 years I've been using this. And again, my recommendation is not to get overwhelmed with the notation because it uses a very old notation, but section numbers are wonderful for. That's exactly what we have been teaching, or the intention is to teach, but it is so huge a list that everything cannot be covered. But you can go through it. Oh, we have done this, we have done this. Probably we do 10% of those section names. I think that's how it works. Probably sometime. Yeah. Oh, Webb, how do you find those books?
Yeah.
There is this, I haven't checked myself, check out archive.org. They say that after about 70 years, according to, if I'm not wrong, like according to US law, the copyright is no more valid, but I'm not very sure about that. Don't quote me on this. So most of these very old books are available in here. It's also available for download. But what I did was I just bought them because they're really cheap. But from my perspective, cheap. I mean, money is always dependent on what. So they're in the order of 10 to 15 or 10 to $20 each. But remember, these are more volumes, and Maxwell's is I think 2 volumes. I don't remember. Yeah, I recently, like 2 years back, I bought a few of them. There is also Thompson and Tate. There's natural philosophy, but let's not give too many books. This is what I used Heaviside significantly in the like 3 years back, and recently I've been reading Maxwell. Or by reading, see, I don't get so much time like you guys. I just flip through the pages. I get ideas, and then I try to work out something. That's what I do. Okay, so Jordan, is that reasonable?
Yeah. I think that's reasonable.
Yeah. So
I'm just trying to figure out how to become, like, how to read an autonomous question that doesn't really have direction. So usually when you give homework, there's a lot of direction, and here's this step, this tells you this, what does this mean? Do this next step, prove that this is, the next step. Whereas a question on an exam might be a very autonomous question that asks one question with no direction. So I guess you formulate, which is very helpful in learning. I will say that the way that you ask questions on homework is helpful. But I need more practice on those questions that don't give any sort of input into.
I agree. Yeah. This is a challenge I also have. But I would say Schwinger is the first book. Like, that's because I have learned it from that. Like, Milton, one of the authors in that book, was my PhD advisor. So I have sat in his course more than once, like you guys are sitting in this. So I used to just sit in the course. So, and I have used those styles in my research. So I know a lot. I don't want to say in and out of that book, but I know the great detail of that book. So of course, that book is the primary resource. If you want to use one book, then that's what it is. But then one book's often is not. Or this is what I said. Look at the table of contents of these old books. Hopefully this will help. Maybe from next year onwards, I should just put that in my webpage just to see these are the problems you can work out kind of, or at a homework level, these are the problems you can do. So it's kind of a good list. It's just their style of working or their style of publishing at that time that section numbers were full sentences. So that's what I'm trying to encourage, not the book itself. Book might be hard to read. I don't know. I like them. I like old books in general. Even if any other subject, I tend to use a lot of old books over new books. Notations are a challenge, but if you cross that, if you get used to that thing, I like reading the ideas. They really describe the ideas very well. These days, the notations take over and the ideas are lost. So, but that's my feeling. I'm not saying everyone thinks differently. So that's fine. Okay. Okay, let's proceed after 25 minutes. So, but these are all necessary also, I suppose. So good points. Okay, so we did start on macroscopic electrodynamics. So we have done a lot about charges, point charges, but now we want to talk about materials. Like how do you by macroscopic, we mean lots of charges and basically a continuous set of charges. So in general, so this is called macroscopic electrodynamics. Like that means to say that we should be able to differentiate between a wood and a silicon surface and a metallic surface, like at least at a very broad level, not at a very detailed level, but using one explicit property of the material, we should be able to differentiate them. And the property we will use to differentiate is, remember, these are all neutral materials, so we cannot use a charge as our property of the electric phenomena. Instead, we use dipoles. So we will talk about dipole moment per unit volume. Like we have talked about charge per unit volume. Now we will talk about dipole moment per unit volume. This will be called P. And so we are doing statics. So in general, this can be time dependent also, but we're doing statics. And this is what, that's it, I guess. Yeah, we'll come to the details later, right? So we're going to talk about dipole moment per unit volume of a material, and we will be able to do most of electrodynamics using that. So let's see how do we motivate that. So we have already studied what a dipole moment is, what a charge is. Oh, I should say that I typically do this. Again, if you see chapter 5, I think chapter 4 or 5 of Schringer's book, they derive this in detail, a pretty good detail, and you usually cover that in the course here. It takes about 2 lectures to derive the Maxwell's equation, starting from microscopic level and basically average it out. Do you guys know what is kinetic theory of gases and thermodynamics? What's the relation? Do you know what is kinetic theory of gases? No. So basically, if you understand thermodynamics, is basically deals with the average properties, like temperature, pressure, and volume. But kinetic theory of gases is arriving at the same equations, but from a microscopic level. You take care of all the atoms, 10 raised to 23 of them, but then you give a distribution to them. You say that most of them have a distribution like this, and you average them out over 10 raised to 23 molecules, and then you get something macroscopic. Macroscopic is something like a centimeter long, or even probably micrometer long. Objects will be macroscopic, significantly larger than the atomic size. So that's the idea here. We know how to deal with charges now, but we don't see charges too much in daily life. We see metals and silicons and so on. And we would like to characterize these materials with a reasonably known property, and that is going to be polarization. And in fact, it will become a dielectric constant. So we'll define those quantities. And then how do we do electricity? That's how we do it. Efficient problem? Okay. So that's the theme here. So let's begin with an atom, right? So let's begin with an atom, right? Just an atom. So the hierarchy would be, we'll first discuss an atom, then a lot of atom, or a lot of first less charges, right? So there are lots of charges, preferably neutral, right? Give you an atom, and a lot of atoms gives you a material, right? That's going to be the simple idea. And we will get the simplest model for that. That will be dipole moment per unit volume. And about the model itself, we will discuss in the next two classes. That's where the Kramer's chronic relations and all come in. So that's kind of nice things there. They're called dielectric models. And the same thing, I should say, if you're doing research, the same thing in magnetism is not very easy to do. It took a pretty long time to settle in. I think it surely waited for quantum mechanics and 1950s and 1960s. And that is what is even today an active research area, building models to understand magnetic properties of materials. But remember that magnetic properties of a material are usually significantly weaker than electric properties of a material at atomic level, especially if you're talking about induced phenomena. We'll talk about what an induced phenomenon is. Permanent magnets are strong enough, but typically the induced phenomena is significantly weaker. Okay, so charges we know. So let's talk about an atom. So an atom is basically, in general, a lot of charges, right? So there's a positive charge here, negative charge here, positive charge here. Right. And did I count this curve? So there's 7 of them. Take one more there. So there's positive more. Okay. So that's an atom, let us say, randomly situated charges, and each of them has a charge Q1. This could be nuclear, a proton, or an electron, or a neutron, right? Those are the possibilities. And let's say its position with respect to some origin. So there is an origin now. Like there is a coordinate system, which need not be inside the atom. Typically, that's not easy because if there are lots of atoms, we don't want to give preference to any one atom. So it is somewhere outside, and that's your distance R1. And that's true for each one of the charges, Q1, R2, and so on. And we do know that the total charge for this, so total charge Q will be equal to Q1 plus Q2 plus so on till Qn. And since we are talking about neutral materials, we would like this to be 0. We will say that this is equal to 0. Right? That's the characteristic we are talking about. If it is not 0, that's okay. That then we attend to it like the way usually we do. That is a charge in the system, but we are talking about more than going beyond that charge. And dipole moment, we said is should I say P or P? I think P. So it's Q1 R1 plus Q2, oh, no, not Q1 R1, right? Because I said my origin is not, like Q1 R1 will be with respect to this, this origin, right? So let's say that is an arbitrary point again inside of the atom. I don't know what that point is, really truly arbitrary. So that's R. You can say that's a reference point inside of the atom to specify the position of the atom itself. Like later, so first I'm going to talk about atom, then I'm going to talk about material. When I'm talking about a material, I would like to specify where the atom is. So this will be a position, a point referencing the atom, but that is not a special point. We are not saying that that's a nucleus or anything, but some arbitrary point inside the atom or even slightly outside the atom. So that's your R. Then all my, so if that is my reference, I measure my distances with respect to that point. So it is R1 minus R. So my dipole moment will be Q1 times R1 minus R plus Q2 times, oops, that's not the vector, R2 minus R, and so on, right? Goes to n or as many as there are. And we immediately notice that this is Q1 plus Q, sorry, wrong. It is Q1 R1 plus Q2 R2 and so on. And that is the quantities that relate to capital R come with the coefficient Q1 plus Q2 plus so on. And R, right? You can factor something like that. All the terms with capital R have a Q1 plus Q2 plus Qn coming in front of it. But this is equal to 0. Because the total charge is 0 because our atom is neutral. So our dipole moment, what it says is that it is independent of our choice of reference point, which we already stressed on when we were talking about multiples. Right? So that's a property of this atom. And as I have pointed out, when you're talking about a material, charges are not the important ones. It's a dipole, next one, right? If you have two atoms, how do they interact? They're neutral, right? If they're relatively far, they won't interact at all. So it is the dipoles that is making them interact. Again, what we're not doing here is that ionic interactions, right? When they get very close, then they behave like ions. We are not dealing with that. This is a simplistic model, but you'll be surprised how far this goes. This is even now the current existing grade among the good models. But for example, if you have to do ionic interactions in chemistry, this might be really tricky. There, the charges really play an important role. There, it's probably not okay to assume that 0. So that's our simple model, and we want to average this down. So how do we? So our goal is to find. Okay, charge density is 0 probably. So what is the next one, right? What is the one beyond that? So let's write the force equation. So let's say force on this atom, let's say force on the atom will be equal to a lot of, and let's say that is this whole atom is in an electric field. So I have to exert a force on this, right? So that is electric field in here, which is not uniform. Right? That is a non-uniform electric field, but we know the electric field completely. Right? So the total force it will exert is sum over I times Qi times electric field due to it is the electric field at the position of charge I. That's how I would say that. in principle, since we have not been restricting ourselves to electrostatics too much, we should be able to write this magnetic force also and get the macroscopic equations completely. That's what I typically do. It takes about 2 lectures, but I'm kind of jumping ahead, seeing that I want to do something else in the course later on. So I would encourage you guys to read, I think it's chapter 4 or chapter 5 of Sugar's book for seeing the rest of it. And it's not, it is vector calculus wise a little elaborate, but ideas wise pretty simple. Okay, so do this. Now this is electric field. Now this is the approximation we are making. We shouldn't expect that we are going to really exactly do this in a very clear manner. So we are going to use approximation. So what is approximation? We are going to use the electric field at this point is different from the electric field at this point, but they are relatively close. They are approximately the same, and it is possible to expand with respect to the, or expand as a Taylor expansion around. So that's what it's. It is different, but it is only slightly different. We can track it. So the electric field at the electron site of an atom and the electric field at another electron, they're close, reasonably the same, but different. So that's what we would say. That means we have to expand this out, right? Then you expand it about what point, and that's where this point comes in, this electric field. So that's an arbitrary point. We will expand it about that point. And so if you want to talk about positive charge, we say electric field. What is the electric field of this that this charge is experiencing with reference to this point? Like it's not that we are going to use the electric field at this point, but what is the effect? What's a small change in that effect? So that's the idea. To expand this whole thing out. So this is I. There are many electric field each point. So expand each one of them out, and we would say this is electric field. Ri is I think we what do you say this? Capital R plus Ri minus capital R. So this becomes my reference point, and I'm saying this is small. Now you would say small, whenever we say small, some quantity is small, it has to be small with respect to something. So that means there is some characteristic length in the problem. Like in this case, it could be the size of the atom itself, and these distances are small compared to that distance. Or let us say the distance between two atoms, that could be a good distance, and these quantities are small compared to that. So usually you say R, so the conditions would be R minus R, Ri, and R is small compared to the characteristic length. That's a very, since we don't know which material we are talking about, pick any material and look for some characteristic length in the material. We are also using the fact that all these motions, so we are going to keep a time dependence, even though in this analysis that won't come in too much. When you do both the magnetic case also, we also want to say that the velocities of this individual charges is very small compared to the speed of light. But this doesn't play a significant role in what I'm going to do today, because it's going to be a very simplified version, extremely simplified version. It's only 20% of what the whole thing is. So expand this out. So this is I times Qi times electric field at point R. And now I need to expand that. When you expand it, remember in vector calculus, it is 3, the gradient comes into picture, and this dotted with the gradient. So there's already a Qi. This is the small quantity I'm expanding about, dotted with the gradient. operating on the electric field. And now I have to evaluate it. At which point am I evaluating? This is at R. We did similar expansion when we were doing multipole expansions. It's exactly the same. Higher terms, right, but we are going to neglect those quantities. Higher terms, but we are neglecting those. Notice this is independent of the position of the charges, so that can come out of the sum. So we have electric field, point R, times the sum of the charges. And the same thing here, the sum goes only till this point, right? If I were to stop the sum here, this rest of the quantities does not have any I dependence, the position dependent of individual charges. So this is only the charges that's coming in. And you see that, oh, that's a dipole moment, right? That's a dipole moment. And this is 0. Right? This is what would have dominated if there was a charge, then we say electric field at the point of the atom times the charge of the atom. But that's 0 for us since the atom is neutral and this is the dipole moment. And you see that this is dipole moment dotted with this is called a directional derivative, and this should be familiar, right? Is that familiar? Where did you see this recently? In the exam, right? So I asked you guys to show that the force on a dipole is something, and then I asked you to rewrite it in a certain way, right? That was involving this. So basically, this from this point in the few steps is what the solution of your exam is, which is basically what the force. How can you remember? So the idea is okay. So let's stop the reference to the exam there. But now what we are saying is that the force on an atom, the leading contribution is from the dipole moment of the atom. And the reference is to the arbitrary position R we chose. That's the electric field that is coming in here. There will be higher quadrupole moments, but we are neglecting that, right? Under this approximation. So it will be very good approximation not to include that. That's good enough. In principle, we can work with this, but we are typically interested in energies, right? More than forces, we are interested in energy. And why is that? Why would you be interested in energy more than a force? If I were to make that statement.
You know, it's more fundamental, right?
In Newtonian physics, it doesn't come out like that, right? Is it more fundamental? Because we begin with forces, correct? At least in the modern way of treatment, we do forces, and then we show that, oh, there is an energy also. You can flip the whole thing. You can start with energy and then get the forces. Either way will work. What is more fundamental? Yeah, these days, many people might say it is energy, but not necessarily, right? I mean, at least in Newtonian physics, it seems like you can get one from the other, then why is anything more fundamental? These days we say it because Lagrangian, there are ways of interpreting things in terms of Lagrangian and Hamiltonian, and that is seems like it's more fundamental, but not necessarily. It's not a real clear picture. But then still, Hamiltonian plays a big role in the whole of physics. And where is that? Where does it play a very important role? Where do you see the Hamiltonian? You know what is a Hamiltonian? Yeah.
Quantum.
Huh?
See that in mechanics. That's what you use to describe.
So basically, Hamiltonian is the official name of energy, if you want, or not always. Energy and Hamiltonian are not always the same, but most of the time, if it is time independent, it is the same. And you say it is classical mechanics that you see Hamiltonian.
Yeah, we covered it.
So let's
at the end of
quantum.
last semester.
Tell that again, Jordan.
We covered it at the end of last semester when we did the momentum and the Hamiltonian.
That's correct. But if you notice that in quantum mechanics, if I don't give you energy, can you formulate the problem? If I just tell you that the force is given to you, you cannot formulate the problem. We don't know how to do quantum mechanics without the energy, without the Hamiltonian. That's the only way we know how to do quantum mechanics, and that is using Hamiltonian. It might be a little overstatement. You can do it this way, that way, but that's, I think, for a teaching level to emphasize a point, that is correct. So energy, if you don't have the energy, then you don't know how to begin. Like if you think of Schrodinger equation, what goes in there is a potential, right? If you don't know potential, it doesn't help. So in that sense, so that was just a statement to say that the force is okay, good, but it's nice to know what is the energy. And force and energy, are they always related? When are force and energy related? They are related only under special circumstances. What is a special circumstance? What's the word for that?
For conservative forces.
Well, the conservative forces, that means there is no dissipation. Right? Pretty much neglect dissipation itself. And at microscopic level, it is okay to see that most probably there is no dissipation unless you're talking about radiation and so on. So Maxwell's equations are conservative forces. And again, we haven't shown that. So probably when we're doing magnetism, we will probably show that very, very clearly. Yeah, actually extra credit, right? So extra credit. Right. If you have a charge in a magnetic field, so let's say magnetic field, and if there is a positive charge moving with velocity v, what does it do? What will it immediately start doing? Right. Start going in circles around the magnetic field. Can the magnetic field or magnetic force do work on the charge?
No.
Is that clear what I mean by work?
No, it can't.
No, good. So work is, if you remember, force dotted with the displacement. But whenever you're going in a circle, the force is inward and the displacement is tangential. So that's always perpendicular. So you cannot do any work. So you cannot change the kinetic energy of a particle using magnetic forces alone, right? Is that true? But if you in real life look at it, I can take a magnet and I move my magnet, one of the magnets, the other magnet will probably move, right? So it seems, so what does it mean to say that there is no work done? Eventually it is going to be a magnetic field. Like the other dipole is also built out of charges. So if one charge cannot do any work, how do you do any work? So, and this seems to be a statement of conservative force. Like only if this is true, then can you say that Maxwell's equations are conservative. So kinetic energy cannot be changed. Kinetic energy, you cannot change the kinetic energy of a system using magnetic fields. Right? That seems to be what is true. Then how do you move things using magnetic field? We do move things, right? Like the example typically given is that you take a huge magnet, take a car, you can lift a car and take it and put it in some other place. The magnet is doing the work most probably. Right? I always say that, yeah, eventually it is something else, but at some stage it is a magnet, that magnetic field that did the work. So how do you answer that question? So that should be a conundrum. You should be surprised at that. And you probably may not get the answer, but we attend to it when we're doing magnetic field in a very clear.
Like the potential to work on it.
That's very good. Yeah, that's the answer to that. So I'm going to use that answer. So vector potential to work. No, vector potential is not a force, right? But I think the key to this point is that magnetic field does not change the kinetic energy, but it can change the momentum. So it changes the momentum, and we don't see that in elementary descriptions because it needs the vector potential. So we have to introduce the vector. So the key to this is to try to read, and resources here are very they don't do a good job. Like many of them, I don't want to explicitly say wrong. So be careful about reading the resources out there. So read good resources, I would say. Authoritative resources here. So look up vector potential and momentum. So vector potential and how does momentum change? Or what is electromagnetic momentum? That's what you can ask. Like momentum is mass times velocity, typically we say. That's no more the momentum. When magnetic field is there, it's no more the momentum. Right? So I think, the word is canonical momentum. Read up canonical momentum. Canonical momentum. Okay. So that will give you some information in there. But again, use authoritative resources. Be careful. At least you don't make up your mind using other. Do read about other things, but don't make up your mind using every other article. Okay.
So I have a quick question.
Yes, please. Yes.
So say I go to the gym and I do bench press, right? And I
repeat that. Sorry, I missed.
Say I go to the weightlifting gym and I pick up a bar off of the, let's say I'm doing bench press where you lay on your back and you press the weight. You know, you let the weight down to your chest and you press it back up. Technically, the work done is, there's no work done because you're.
Okay. So here is how I try to resolve this thing. Work done is slightly ambiguous. Work done by what? Correct? So define this expression here as the work done by the force on the mass m. By the force, not by you, not by your muscles or anything. Work done by the force.
Okay.
And then there is a lot of clarity. Then there is usually no ambiguity. So here what we are saying is that the work done by the magnetic force on the charge.
Okay.
So eventually, you can always say, for example, I eat a lot. I lifted my, let's say my bag from the parking lot to here. Did I do any work at all or not? That's very vague. Who is doing this work, right? Of course, I have done any work, but then I go up the stairs and come down the stairs. Now, I know that gravitational potential energy has not changed, but I did do a lot of work, right? It seems like I did a lot of work, but that is me. That is some muscle doing, so muscles are involving forces. That's a lot of complicated things. But forget those things. What we should ask is, what is the work done by the force of gravity and the potential energy are connected? No ambiguity there. Work done by the force of gravity when you go up the stairs and come back is zero. You can go to another galaxy and come back at zero.
Could it be because we're looking at the net work done, not like the instantaneous work done?
True. So you have to split it. So that's why it becomes very unambiguous if I say work done by the gravitational force. That's clear. One piece out of the many forces that's acting. Other forces, I don't even know what other forces are acting on it. Like you bring in muscles, everything, it's too complicated. But if you say gravitational force, we understand very well. No ambiguity there. It is a conservative force. It is zero. Right? If you go around in a circle, that's zero.
No, I meant to say let's say you move upstairs, you do some work at that point, and then you come back again. The net work done is zero?
No, probably friction. I lost force.
Let's say there's no friction.
Net work done by the force in the sense
yes.
Acceleration.
But
Probably.
There's some work
That's
done,
correct,
right?
that's correct. Yeah.
And when you come down, that work is negative to the work done.
Sure, that's correct. But it's not very useful. Right? Yeah, correct. That's correct. I would say I'll give it. That's truly correct. But it's not very useful, I would say. What can I conclude from that? Can I learn how much energy I lost? Can I learn how much energy something did? Probably it's not very useful. But yeah, in the beginning, especially when we are learning Newtonian mechanics. So again, we should be careful. There's thermodynamics here, right? So I would say there is mechanical energy being lost into, yeah, be careful, cushion it. Like when we do Newtonian physics, it is true that, yeah, mass times acceleration is equal to F1 plus F2 plus F3. Integrated, I get change in kinetic energy is the work done by all the forces. What about the thermodynamics? Where did that force come in? Like, where are those things? So I would say cushion it. There are contact forces, everything there. I would cushion it. Like radiation, where did that go? Some light was lost probably because I rubbed my shoes on the floor. I don't understand that radiation very well. So I would say don't buy it so easily at this level. Yeah, I won't tell this in my undergraduate course. I'll say that yes, there is conserved. And there also be a little careful. We said mechanical energy is conserved. Raw Westerland. Okay, so yeah. So does that roughly help? Any more comments on that? It is important, and it's even now, I would say, especially the work energy loss dissipation forces are very important. That is how actually the whole quantum mechanics began. Einstein questioned these things as to what kind of dissipation is happening. And that is what led to the black body radiation. So I would say it is important, one should ask, but it is much easier to work in conservative systems. Much, much easier because you can use the force and conservative forces. And that's what 99% of the research or the main, whenever we're talking about applications, we stick to that because there is a lot of understanding on that. But if you want to question the fundamentals, then I think one should question how do we understand dissipation. That's my personal view. You guys should think about it. Okay. Anything else I should address? Okay, so if I proceed, so I was actually motivating. Yeah, this is the force, but what is the energy then, right? How is the energy related? If it is a conservative force, we know that force is equal to negative divergence of potential energy, right? If it is like for conservative forces. So if I can write it like this, then it is conservative, otherwise it's not. Right? And then we immediately ask, what are our equations? And remember, we are in this derivation, I'm using electrostatics. But in general, it doesn't have to be electrostatics. And that's why I said I'm doing a simplified version. Chapter 4 does a more involved, and usually I do that in 2 lectures. This time I'm compromising. So if we are doing electrostatics involves del dotted with E is equal to, this is microscopic level, right? So this is charge density over epsilon naught. Like microscopic Maxwell's equation remains the same. Cross E. And what is that equal to in electrostatics?
0.
That's 0, right? It's general, it is the time derivative of the magnetic field. It is 0 if it is electrostatics. But then that tells you if it is 0, only in electrostatics, this is equal to negative gradient of an electric potential. If it was not that, what is the correction to this? If there was a magnetic field, what is the correction to this? In general, there is dA by dt, right? That's a vector potential that comes in. That's the magnetic field potential, potential associated with that. But again, we see the time derivative there, so it's not there. we are not considering that in this elementary discussion. So electric field is negative gradient of phi. So let me go to the other board now. Oops. It was not set. I think I might not reach the top part. Okay, so we have force is equal to negative dipole moment. This is called directional derivative, right? Gradient is in general can be done in any direction, unlike your complex function derivative. This is directional dependent, and we are saying it's a derivative in the direction of the dipole moment. Right? Since we said electric field is a negative of an electric potential, so this becomes plus, right, with gradient of phi. So this is a cyclic. Notice, otherwise the challenge is that this gradient is dotted with the dipole moment. Right? And at the end, I would like to have the gradient of potential energy. Right? I have to release this from the dipole moment. That's a challenge in the problem that was given in the exam. Right? This gradient is cannot be the same as this gradient, because this is dotted with dipole moment. It is taken up, right? So where is that dipole? Where is that gradient? Is it conservative? So that's a challenge. But then you realize that in electrostatics you can do this. Now, once you have this, now the question is, can you bring this out? And it seems like you can do this because two gradients commute. But this dipole moment, one has to be careful. Now you ask, does it depend on the gradient? This is the property of an atom, right? We are talking about the atom itself, and it's a property of an atom that doesn't depend on coordinates. So it's like saying, does your mass depend on the coordinates? It does not. But if you're talking about a material, then maybe it does. At each point there is a dipole moment. There are different atoms, but this is the total dipole moment of the atom when we're talking about the force on the atom. So this does not depend on it. So this can come out all the way. That's gradient of dipole moment dotted with phi. And then you realize, oh, that's again the electric field, but this time it's a different electric field. If you notice, this is an electric field. That gradient, you pulled out the gradient, and now you're providing the gradient to the electric field again using this. So it's a kind of a catch in there. It seems like, it's not obvious. So that's again the electric field, provide a negative sign. So this is E with E. Did I say that correct? Probably not. What did I mess up? This is correct. This is correct. But this is wrong. What's wrong? Oh, that was a plus sign. I didn't have to start with a negative sign. That was a plus sign, correct? This is plus sign. So I copied it wrong. So that means this will be a negative sign, and this will be a negative sign, and this will be a plus sign. Sorry about that. Okay. But if we want to compare if you want to extract the energy out of it, we have now written it in terms of a gradient. So the energy, potential energy of an atom inside an electric field, which is that of a dipole moment, is negative dipole moment with respect to electric field. This is what you would plug in if you want to understand how a dipole moment of an atom interacts and what are its energy levels. This is what you have to substitute in your electric potential or potential energy when you're doing the Schrodinger equation, right? Schrodinger equation, usually in the early stages we do in a box and so on, but the interesting ones are when you have a hydrogen atom, right? And if you keep an hydrogen atom in an electric field, this is the potential you have to change, right? That's your potential. The dipole moment of the atom and the electric field that you're exerting from outside, and then you can ask how does the energy change. This is not energy, remember, this is electric field. Okay, so that's your potential energy. That's just a side track. We are still working with our forces, right? So that's your forces. Now we have an atom. Now we can go to the level of material. So a material, force on a material is the sum of a lot of atoms, like sum of the forces on atoms. Right. And how do you do this sum in a reasonable way? So we have to introduce a property. Notice now we're talking about 10 raised to 23 atoms, and a good thing we already have, and this is what you do in kinetic theory of gases, is you bring in one or any transport phenomena. Like you do a lot of properties you study at a macroscopic level. There is one common feature in all, and that is a number density. You ask how many atoms or how many charges are there in per unit volume. That's one property that is used to go from microscopic to macroscopic. So we will say that, for example, if there is a small region where there are no atoms, there is no force, right? So instead of this, we go to an integral because it is reasonably continuous. So this is d cube x. There is a number density, that's n of r, times the force on individual atoms. So, or individual charges also you can say, but we have already taken care of that. Right? So this is n of r is number per unit volume. And that information usually is easily available. It's a very well studied topic. And that is where statistics comes in. This number density can be read out using whether you're using Fermi-Dirac statistics or boson statistics, it matters. So that plays an important role in that. So that's, we will say that that's given to us, and then put it in there, right? Or whatever we have for the force. So that's d cube x times n of r times we have dipole, right? We said d dotted, so we want to go back to our expression there. So this is d dotted with, okay, that's our first expression here. And now I switched my position from R, capital R to R. So this is now R. So this is the position of an individual atom. This is the derivative with respect to position of the atoms, and this is the number density. And you get this quantity here, and that's what is our polarization. So you notice that a number density times something will be our macroscopic property of that. Also, polarization will be described as polarization or electric polarization. 3 minutes. We will define that as P. We are doing statics. In general, this can be time dependent. in that case, the magnetic dipole moment also shows up, and that's equal to the number density times the dipole moments at each point. So I should actually say, notice this shouldn't be confused with dipole moment being R dependent. It is the each volume now there is a resultant dipole moment. Right? So that's R dependent. And this is very simplistically speaking, this is dipole moment per unit volume. Which makes sense. In multiple expansion, if charges are not there, the leading is dipole moment, so then we talk about dipole moment per unit. With that in mind, now let's talk about what is a force, right? We still are not done because we had a goal here, right? So what was the point? So we have P, let's take 3-4 minutes extra. This is P dotted with gradient of the electric field. And this is also R dependent. I can do an integration by parts to get the derivative on the other side, and that is minus dqx times divergence of the polarization with the negative sign in front times the electric field plus a surface term, right? Every time we do a differentiation by parts, there is a surface term that dots with the whole thing. Right? P of R times the electric field. But this is zero. We are saying this is over all space if the material doesn't extend to infinity. So this is equal to 0 at infinity. So that doesn't contribute. So we have this as our expression, and that is exactly what we want. Why? Because we know, so if this was a force, remember force is charge times the electric field. Right? If there was a charge, it would have to say charge times the electric field. But if it was a continuous distribution, you would say force per unit volume. Then you would say this is small f, that's force per unit volume, which is a position dependent quantity. We did this in conservative forces, and we said this is charge density then, times the electric field at a certain point. Right? That's a more descriptive equation. And now, and then the total force will be integral, right? So in that case, the total force will be equal to integral dqr times charge density times the electric field. Comparing these two equations, it seems like the material acts as if there is charge on it, right? But the charge is coming from the dipole moment, so that we will call it the effective charge density. Effective charge density of a material is given by negative of the divergence of the dipole moment density. So if we know the dipole moment density, take the divergence of that, interpret it as charge, and do your old physics. We know what happens when there is a charge. So a dipole moment, the divergence of that acts like a charge for a material. And this is a position dependent quantity. And we will do examples where we have this polarization and what will be the electric field associated with it. So we do simple examples where we can use all of the earlier results. We know how to work with charge density. So we just have to start from here and get here and then use our old results. Right? That's what we'll do. Thank you. And I cross the time. But next time, there is homework where you have to deal with, I give you this P and you have to calculate this. That's the first problem. The second problem is where I give you P and you have to calculate electric potential, electric field, everything. Right? And on Monday, we will do this for a sphere. If we have a polarized sphere, how does the electric field come up? Which is a reasonably standard example in textbooks. Thank you.
Thank you.
Yeah, thank you.
Thanks.
Bye, Alia. Bye, you.
Bye.
Bye.
Bye, Jordan. Everything. Are you talking from hospital, Jordan?
No, I'm driving home from.
Driving home. So you're in the car. Nice.
Yeah,
Okay.
my wife is driving right now, so I got to listen.
Okay. Okay. No problem. Yeah.
Alrighty.
Yeah,
Bye
take
bye.
care. Yeah, I hope everything works out for you.
Yes,
And
I think it's signs are good at this point, so that's good.
Okay. Yeah.
Bye bye.
Yeah. These are tough things when you don't
Yes.
know exactly to go with. Yeah.
Yes, very. It's you.
Do your best.
You just think it's not a problem for a long time until it is, I guess. So. Alrighty. We'll
Okay.
see you. You'll see my face next Monday. Bye bye.
Take care. Take care. Yeah.
See ya.
Okay. No worries.